ISMA 21 in postings, and at the reference to ISMA accounts via at ISMA COMF. In addition, there are individual Discord channels for the session, as well as each paper for discussion with authors during the week and beyond. And for the viewers on YouTube, you also can register to join the interactive elements of ISMA 2021. And after the session, all attendees should move into Gather Town to talk one-to-one with authors in Q&A rooms. Links to Gather Town are provided in Discord, Gather Town menu guides, and FAQ. Okay, and then the first talk is detection guided 3D hand tracking for mobile AI application. The speaker is Yunrong Ce. So you can share your screen.
Yes.
Okay.
Can you see the screen?
Yeah.
Okay.
Okay. Yunrong Ce is a research engineer of Opera Research Institute. His research interests include augmented reality and virtual reality. Okay, so let's welcome his presentation.
Hello everyone. Today I'm going to talk about our detection guide hand tracking methods. I'm Yunrong. I'm from Opera Research, and hand-based interaction is a natural way of communication with the machines. Real-time hand tracking is key to 3D perception of user hand and reality interaction. Current work estimate hand posture with a deep or color image camera. Deep-based work can be roughly grouped into two kinds: data-driven methods aim to learn a function from training set and map input image to hand pose. Model-driven approach estimates hand pose by fitting a parametric hand model to input. However, current deep sensors have a narrow field of views or limited working range. Color-based work estimates hand joints with deep networks. This work may not time effective and require expensive computing resource. Human hands are highly articulated, appear in various orientation, shapes, occlusion, and motion blur. Further improves the variation in the appearance of hand. Achieving real-time and robust hand tracking still has many challenges. In this paper, we present a detection guide standing hand tracking methods that allows flexible hand-to-mobile interaction. Our hand tracking methods consist of a set of learning-based detectors and a model-based pose solver. First, we propose a hand detector and a joint detector to locate hand and joints. The former aims to detect the hand bounding box. The latter receives the hand region as input and output to the joint position. A flexible and robust hand-based interaction interface need to acquire more details of hand. We recover 3D hand posture from the 2D joints. This process is formulated as a non-linear list problem and search for the best pose by optimization. This paper here we show our pipeline. First, in the pipeline work, we extract hand part from the input with the hand detector. The key insight of our hand detector is incorporating a novel attention mechanism to capture the non-local context dependence between hand and joints. To be more specific, we embed attention augmented inverse bottleneck block model. This is our network. It's more like the focal loss. After obeying the hand region, we feed the region to the joint detector. The detector is inspired by DenseNet. Each level obeys additional input from all preceding ones and propagate its own feature map to all the subsequent level by a channel-wise constraints. To compare with the methods directly redress the position, the head map of each joint can indicate whether the joints are in state of tracking or not. To speed the inference of the inference on the mobile device, we adopt a semantic encoder and decoder. Starting from the estimate 2D position of joint, a inverse kinematic-based multi-stage optimization, which carefully balances depth fitting and period limits, is designed to recover the final 3D hand posture. The goal of this stage is to find a pose that best matches the 2D joint location. We align the estimated 2D joint and 3D hand model by a data constraint term. Due to the non-convenience of the problem, only minimize the 2D to 3D matching error may result in unrealistic pose. Therefore, we regulate the optimization with the center of periods like collection, joint rotation, and temperature to ensure the reason is flexible. Here we show some reason. The reason of 2D joint detection and 3D hand tracking reason in a mobile device. The left one shows the 2D joint detection reason. The right one shows the 3D tracking reason on mobile. We recover the video in another phone. We compare our reason to some state-of-art work on CMU dataset. We refer the reason produced by our 2D joint detector as a 2D detector. Our methods outperform them and a 2D detector with a substantial margin. The reason in Yokohama outperform our methods with a large margin. This is due to the novel architecture, which combines the 2D and 3D joint detector and mesh recover. However, such a heavy network cannot achieve real-time on mobile device. We also conduct a comparison with the hybrid methods on OCTP dataset. The proposed hybrid our work is a hybrid. We also combine the proposed hybrid methods with a baseline without a sharp. It is shown in the green one. Without the sharp, we only optimize the hand pose. Our methods result in more occurrence due to the joint of the optimization stage. Furthermore, the reason of our full fitting is superior to that of without a shape, especially when the hand is in state of tracking loose, which shows the effectiveness of our search. We list some fitting reason without period limits from left to right. We show the reason. We show the reason of only dead fitting. And the middle one shows the dead fitting with the rotation term. The right one shows the fitting with the dead term, rotation term, collision term, and temperature term. With the tracked hand 3D hand posture, user can rotate can rotate the visual object we show a simple demo in this video. With tracked standing posture, user can hold a visual object on plan. User can see when the hand is close to the camera, the visual object is become larger. Thank you, everyone. This is my.
Okay, thank you, Yuno. So we still have a few minutes. So is there any questions?
So I have a question. In your slides in the classification, like your network, so you classify. I don't know what you classify. So it's the gesture or something else. So can you go back to your slides in the network?
Yes. In our work, we use a hand detector to detect the hand binding box. And another
so,
network.
I mean the classification. So in your results, you have a classification. What's the classes are?
I classify the hand gesture only with some rule-based methods, like like the gesture catch or pinch or grab. If the fingertips the distance of the thumb finger or index finger are closed, I think the gesture is grab or pinch.
Okay. So you predefine some gesture.
Yes.
Okay.
Yes.
Okay. Thank you.
Okay. We still have 2 minutes. So I see a question. In passive work, does the hand tracking work with any skin color? It's does the hand tracking work with any skin color? It's a question from the attendee. Yeah.
Yes. The hand current work, the hand tracking works on any color. It depends on the training center. It depends on the hand detection training center. If the black color or the white color skin is included in the training center, we think the hand tracking may works well.
Okay. Is there any question? So no. Okay. So thank you again for your nice presentation. And then the second talk, the title of second talk is SAR Spatial Aware Regression for 3D Hand Pose and Mesh Reconstruction from a Monocular RGB Image. The speaker is Xiaozhen Zheng. Hi, Xiaozhen. Please share your screen.
Okay.
Okay. Xiaozhen Zheng is a master's student in the State Key Laboratory of Networking and Switching Technology, Beijing University of Posts and Telecommunications. His research interests include machine learning, computer vision, and hand pose estimation. Okay.
Okay.
Let's welcome Xiaozhen for his talk.
Yeah. Hello, everyone. Today I'll introduce our work, SAR Spatial Aware Regression for 3D hand pose and mesh reconstruction from a monocular RGB image. 3D hand reconstruction has been a popular research topic in recent years. It aims to simultaneously predict 3D hand sparse post joint locations. and 3D hand-dense mesh vertices locations. It is an important technique for non-contact human-computer interaction, and it has great potential to apply in VR or AR scenario. We roughly divide recent works in this area into two categories. The first category is regression-based methods. There are also two kinds of regression-based methods. The first kind uses convolutional neural networks to map input images to image features. Then it utilizes those extracted features to regress the shape and pose coefficients of a parametric hand model. The first part of the second kind method is the same as the first kind. It uses a network to encode images to features. Then it regresses the coordinates of post joint and mesh vertices directly from extracted features. The second category is detection-based methods. It uses fully convolutional networks to predict dense belief maps of joints or vertices, and then obtain the joints and vertices coordinates from those belief maps. However, both of these methods are not doing well in balancing accuracy and efficiency. Regression-based methods have two shortcomings. First, they do not fully exploit spatial information extracted by convolutional neural networks. Because they apply global average pooling to obtain low-dimensional features for regression. Those features' 2D spatial information is squeezed by global average pooling. Second, they cannot model the uncertainty of predictions because it directly regresses 3D coordinates. This results in relatively low accuracy. On the contrary, detection-based methods are relatively more accurate because they use fully convolutional networks to preserve spatial information and predict belief maps instead of coordinates to model uncertainty. However, detection-based methods rely on deconvolutional blocks, and these deconvolutional blocks have two drawbacks. First, they require amount of computations. Second, it does not explicitly model the relationships between different vertices that are beneficial for solving occlusions and smoothing mesh predictions. According to those recent impressive works, we summarize that designing a balanced algorithm should preserve spatial information efficiently, model the relationships between different vertices explicitly, and model the uncertainty of predictions. Based on these ideas, we propose a novel framework to solve the limitations mentioned above. To preserve spatial information, we propose spatial-aware initial graph building. To model the relationships between vertices and model the uncertainty of predictions, we propose GCN-based belief maps regression, consisting of adaptive graph convolutional networks for regression and belief maps as regression targets. In general, our method still belongs to regression-based methods. We introduce the ideas of preserving spatial information and modeling uncertainty of predictions into regression-based methods to help design a more accurate and efficient framework. Next, we introduce three essential modules of our framework. First is spatial-aware initial graph building module. At first, we obtain image feature maps from convolutional networks. Then we treat the mesh template as a graph and distribute the extracted feature maps to every vertex with no overlap in channel order. Finally, we get this mesh spatial-aware initial graph for later regression. This way is different from previous methods, either using global average pooling to obtain low-dimensional features or using the same initial feature for all the vertices. It makes every vertex has spatial structure information and vertex-specific features. This spatial-aware graph contributes a lot to accurate and efficient regression. The experiments show that our proposed spatial-aware initial graph building is significantly more accurate than previous methods. Moreover, we can see that the initial graph building way significantly influences the performance, which is overlooked by previous methods. Next is GCN-based belief maps regression module. After obtaining mesh spatial via initial graph, we utilize adaptive graph convolutional network for the vertices to interact. This form of GCN allows the network to automatically adjust the attentions of a vertex to interact with a specific vertex. The short-range and long-range dependencies can be captured in this way without stacking many layers of GCN, which is more flexible and efficient. In the last GCN layer, we map vertices features into 2D latent belief maps and depth maps instead of 3D coordinates directly. This can model the uncertainty of predictions to improve accuracy. From the experiments, we can see that this form of GCN performs better than the common one, that using the fixed connections of mesh templates as an adjacency matrix. Besides, we can find that modeling the uncertainty of predictions performs much better than predicting 3D coordinates directly. Adopting 2.5D belief maps as representation makes it easy to leverage multi-stage architecture to refine the initial predictions. These belief maps can provide rich 3D spatial information and powerful disambiguation clues for further stage network to refine cost predictions. Therefore, we introduced 2D GCN's refinement strategy in 3D hand reconstruction. However, directly using all the mesh belief maps for refinement is redundant and will cause optimization difficulties. Thus, we propose PGR solve this problem. More specifically, we first obtain post-belief maps with the post-labels guidance. Then we use those post-belief maps to provide multi-joint spatial context and the 3D spatial information to perform refinement to obtain more accurate and robust results. Experiment results show that multi-stage refinement is very useful for mesh reconstruction. Furthermore, using refinement with post guidance performs better than using mesh guidance. With the help of these three essential modules, our framework achieves the best performance on 2 online computation 3D hand reconstruction datasets and 2 3D hand post estimation datasets. There is the performance of our framework in 4 publicly available datasets. In the last column of the table 1, we also show the comparisons of the inference speed of our methods with different SOTA methods. We can find that our approach can achieve the best performance while having the fastest inference speed. That is because our network architecture is highly simple and efficient. We only need ResNet 34 with our designed regression module that consists only 2 layers of adaptive GCN. Last, we show some visual results of our method in these 4 public datasets. The right shows all the visual results of our method in actual 3D datasets without using any temporal information or object information. This video is about 2 minutes. Because our time is enough, we can finish this. Because we did not use temporal information, the results there will be some fluctuation. That's all. Thank you for listening.
Thank you. And thanks to Xiaozhen. And is there any questions?
How extractive features from CNN are infused to hand mesh graph? Oh, I'll show the graph. This. We gather feature maps from the convolutional networks, and then we distribute the feature maps in channel order. For example, we can distribute 4 feature maps from the backbone to 1 vertex in the graph. If we have 4 nodes, and we will distribute 16 feature maps to those nodes. Is that clear?
Is there more question? Oh, no. Okay. Let's thank Xiaozhen again for his nice presentation. Okay. Then the third talk is two-hand post estimation from the non-cropped RGB image with self-attention based network. The speaker is Zhou Taoshun. Zhou Taoshun is a PhD student in the State Key Laboratory of Virtual Reality Technology and Systems at Beihang University. His research interests include virtual reality and computer vision. So let's welcome his talk.
Okay, hello everyone, welcome to my presentation. My name is Zhou Tao, and I'm going to talk about the paper two-hand post estimation from the non-cropped RGB image with self-attention based network. Human-computer interaction is an important way for users to perceive and manipulate things and objects in VR and AR. In the real world, we habitually use our own hands to grasp objects and operate equipments. Therefore, an accurate and robust post estimation technology is an important foundation for a flexible and natural human-computer interaction. And here are some examples. The column on the left is where the user utilizes his hand to manipulate virtual objects in virtual scene, such as the piano and the electronic sound table shown in the picture. The right column shows users interact with gestures in AR applications. However, hand post estimation in real time is a challenging task, especially when the input is only one image. The following are some of the difficulties in this problem. The first is hand tracking, how to segment or crop the hand region of interest from the complex background. Secondly, since the hand is a highly articulated object, it is usually necessary to predict the coordinates of joints on one hand to express the hand pose. At the same time, due to the incomplete input data, the similarity and occlusion between the fingers will also increase the difficulty of the hand pose estimation task. The joint move flexibly and quickly, which also leads to an increase in the problem-solving space. Due to the difficulty and importance of hand pose estimation tasks, many researchers have proposed solutions in this field. However, humans naturally use two hands at the same time in daily tasks, and most of the existing works focus on estimation of a single hand. Therefore, A natural idea is to explore estimation of two-hand pose in real time from monocular RGB image. However, more hands, more challenges. Compared with single hand, there are more difficulties in two-hand pose estimation, such as higher dimensional optimization problem, more complex foreground extraction problem, more self-similarities and occlusions from the other hand. Here are some studies on the task of two-hand pose estimation. However, there are still some problems with their method. For example, single-hand detection method cannot work well on localizing two-hand regions, and researchers usually need the dataset contains the data of the hand ROI bounding box. And some of them only focus on pose estimation of interacting hands or two independent hands. However, in a flexible human-computer interaction method, it needs to be able to directly locate the hand area in the input image and be able to predict the single hand and two-hand pose in different situations at the same time. Therefore, we proposed this pipeline to solve the above problems. Given an RGB image that includes one or two hands, our goal is to predict whether there are left or right hands in the input image and to estimate the joint locations of existing hands. Firstly, we construct a deep neural network-based encoder with multi-head self-attention, which follows the architecture like ResNet 50 to extract the feature vector. Then we use this vector to predict the handness, the relative depth, and the joint location by a decoder. The decoder consists of 3 parts, and 2 of them are stacked by linear layers. The last is composed of deconvolution layers and an upsampling block with multi-head self-attention called SRAM block, which we proposed. In both encoder and decoder, we incorporate multi-head self-attention with traditional convolutional layers. Thus, we first introduce the multi-head self-attention briefly. Assuming the input sequence is I, we first calculate query, key, and value by 3 matrices. Then the normal scaled dot product attention is calculated as this. This can also called single head attention. The multi-head self-attention is defined that the QKV are calculated n times with different matrices in parallel, and then the output are concatenated and once again projected to get final result, like this image. Now let's introduce the architecture of our encoder. Since the number of hands and the interaction posture in the input image is uncertain, and there is no information about hand segmentation or bounding boxes, a natural idea is to use the attention mechanism to make the encoder focuses more on the hand area and extract feature vectors. Therefore, we first take advantage of the small respective field of convolutional layers to extract image detailed features, and then we perform the multi-head self-attention operation in the feature map to extract the useful feature information. The first 3 blocks called bottleneck comes from the ResNet. The last block called bot block, and its calculation process is shown in this figure. We use only 1x1 convolution to get QKV instead of the linear projection, and construct a learnable parameter called positional encoding to provide the attention matrix with position information. Compared with only using convolution for feature extraction, the prediction result of our proposed encoder structure focuses more on the hand region. Decoders are usually used to recover joint coordinates from feature vectors. Since the self-attention operation does not produce dimensional information on input or output, we propose an upsampling model based on multi-head self-attention called SRAM block. We first use 1x1 convolution layers to get QKV. The width and height of KV remains unchanged, and the deconvolution operation is only used to double the width and height of Q. This operation is called spatial reduction attention. Since the calculated attention matrix is very sparse, we guess that using deconvolution to enlarge the dimension of KV will bring more useless informations of the joint point coordinates. Therefore, we use a spatial reduction attention to reduce the dimension of the attention matrix to reduce the computational complexity. However, In actual applications, the computational complexity and memory consumption of using only SRA are still unacceptable. Therefore, we further combine the Nystrom former to approximate the attention matrix. After calculating the QKV, we use the adaptive average pooling method to obtain the tilde Q and tilde K, with whose weights and height are much smaller than QK. Then calculated tilde F, A, and B. Then use the SBD method to iteratively calculate the pseudo-inverse matrix of A. The final output is as shown in this formula. The prediction result of using SRAM block and only using deconvolution for upsampling are shown in this figure. We can see that the predicted joint locations are smoother and more accurate when introducing the global information with multi-heads of attention into the decoder. And next, let me introduce the loss function and parameters of training the neural network. For the three types of output, we apply different loss functions respectively, and the final loss function is added by the three terms, and the weights are all one. The learning rate, batch size, and optimizer are shown as above. In order to quantify the quality of the prediction result, we also use different evaluation metrics for different outputs. Comparing with the sorter method, we can see that our method has achieved similar or better result on two test sets, even though the baseline utilizes cropped RGB image. We utilize the test H&M of the interhand dataset to evaluate each part of our network, and we can see that every part proposed in our method has an effect on the prediction result. Besides, we can see from the table and the top two curves from PCK image that our SRAM block does not scale down the prediction effect while utilizing the least time and memory. On this page, we show the qualitative results from our proposed method in different situations, including single hand, two separated hand, interacting hand, and real-world scenario examples. In summary, we proposed a method to estimate hand pose from a single non-cropped RGB image. Through the combination of multi-head self-attention and the convolution neural network architecture, this pipeline can accurately predict the key points location in the hand ROS in real time. But there are some limitations we need to solve. For example, how to avoid the influence of invisible joints on the prediction result. Also, since we didn't utilize the temporary information, and how to avoid jitter results in video. Oh, well, that's all. Thank you. And does anyone have any questions?
Is there any questions? No. Okay, I have a question. So your method can perform real time, right? In your final conclusion. So how fast?
It achieves above 30 FPS in NVIDIA 3090 那个 GPU, and it might be a future work to explore how to achieve real-time speed in mobile phone.
Okay, so you think it's possible, right, to
yes.
achieve real time on a mobile device?
Yes.
Okay, great. Okay, is there a question? Can you explain that? For what did you use loss functions?
Okay.
You can share your screen. Okay, yeah.
We use three loss functions. The first is a binary cross entropy loss for hardness. In our method, we predict three parts, include hardness, relative depth, and the joint locations. And all these three parts can combine to express the two-hand pose estimate. Thus, these three loss functions these three loss functions are used to predict these three parts. The LH means the binary cross entropy loss for hardness, and the rel is the loss function for relative depth, and the L joint is a loss function for joint heat map, and it's calculated as this formula. Do I need to explain the detail about this loss function?
Okay. Is there any more question? Okay. So let's thank Zhou again for his nice presentation. And the next talk is stage special temporal graph autoencoder for hand motion denoising. The speaker is Kanlei Zhou.
I'm here. Wait a
Okay.
minute.
Okay. So Kanlei Zhou is a PhD student in the State Key Laboratory of Virtual Reality Technology and Systems at Beihang University. His research interests are mainly in mixed reality and graph neural networks. Okay, let's welcome Kanlei's talk.
Is it okay?
Okay.
Yeah, I'm ready. Hello, everyone. I'm Kanlei Zhou from Beihang University. Now I'm in the second year of my PhD degree. It's my great honor to present our work at Stage Spatial Temporal Graph Autoencoder for Hand Motion Denoising. During the interaction of AR, human hands play a key role to perform operations such as grasp and rotate. Therefore, accurate pose estimation and tracking can effectively improve the user experience. However, the complex articulation, self-occlusion, and self-similarity of hands makes this task challenging, and prolonged interactions may cause fragile and involuntary handshaking. Moreover, hand-object interaction in MR is extremely unfriendly for patients with motion disorders such as Parkinson's diseases. Therefore, it is of the great interest to develop effective and hand motion denoising method for addressing this problem. Related work. Cleaning motion capture data is the key process. Existing methods for motion data denoising mainly include traditional method and deep learning based method. The former is done by modeling human prior knowledge to the feature and problem by different algorithms such as the skeleton, hierarchy, and filter designs. The latter is done by deep learning frameworks such as CNN, RN, GCN, etc. The latter is done by deep learning method compared with the latter. The former is always depend on some priors and restricted by personal cognitive level. To extract the knowledge directly from the data, the proposed method allows us to introduce some human prior knowledge, the design of the graph, into a deep learning system such that we get the advantage of both. This work aimed to propose a powerful framework for hand motion data denoising, which can effectively extract spatial temporal patterns with remaining structural constraints. Let's see a video about our framework overview.
Hello, Kanlei, can you turn on your camera?
Okay.
Okay. Okay, continue.
Data synthesis algorithm. In this algorithm, we simulate the abnormal hand motion by corrupting the hand joint independently to produce the corrupted data. During the data corruption, the structural constraints between joints are considered to simulate natural abnormal hand motion and preserve the bone length simultaneously. This is an example of data synthesis. A is original data, B is the shift matrix, C is the occlusion mask, D is the shift mask, and D and E is the generated data. Graph construction, neighbor partition strategy. This is an illustration of spatial temporal graph. A is the spatial graph where the red circle denotes the center joint, blue circles represent its physical connected neighbors, and the cyan circles are the symmetry connected ones. B is a temporal graph where the red circle indicates the center joint and blue circles show its temporal neighbors of before and after frame. To determine reliable neighbors, a self-attention mechanism is applied to graph convolution subblock. Architecture, spatial temporal graph convolution block. Due to the success of a stacked hourglass network, a local-to-global scheme can effectively extract global features from the graph-based data. Follow this idea. We propose a novel spatial temporal block with an hourglass structure. Figure 3 illustrates the architecture of a basic spatial temporal encoder block, where both the graph convolution layer and the temporal convolution layer are followed by a batch normalization layer, a ReLU layer, and a dropout layer. Experiment, robust denoising performance. A live demo of hand motion denoising using our method stage. As can be seen, for a deformed motion, STGE worked pretty well. Comparison with SOTA. For deformed motion, our method works pretty well than SOTA methods. We also compare our method on the test set with the state-of-the-art motion capture data denoising method. Although all the methods perform well in most cases, achieves the best performance when processing extremely abnormal motions. We compare our method on test set with the state-of-the-art motion capture data denoising method and measure the above 3 metric for joints across all frame on the test set. Table 1 shows the better performance than the SOTA method. Experiments, ablation study. We perform ablation studies to investigate the contribution of different components of our proposed method on the synthesis data set. All the ablation studies are evaluated on the above three metrics: hand-pulse similarity error, hand-bone length error, and hand-symmetric neighbor error. Table 2 reports the results of ablation studies on attention mechanisms. Both deleting B and C are not conductive to dynamically learn which neighbors are trustworthy. Table 3 elaborates the detailed results of ablation study on partition strategy. A removal of symmetry connected relationships still results in significant performance reduce, indicating the effectiveness of the proposed partition strategy. Experiments, the visualization of our trajectory, motion trajectory and post-error curve plots A, B, and C are the motion trajectory of the index fingertip on x-axis, y-axis, and z-axis respectively. The trajectory of input, output, and ground truth are colored in green, blue, and red respectively. D is the corresponding MSE curve of post-similarity curve, where the red line and the blue line are the post-error changes of noisy input and denied output. This picture depicts the post-error change curve of these consecutive frames, where the red line and the blue line are the MSE curves of input and output respectively. Compared with the input, the MSE curve of the output is almost flat and close to zero, indicating the huge power of our algorithm. The visualization of learned adjacent matrix. A is the original one for the synthesis dataset, including self-connections, physical connections, and symmetric connections. B is an example of the corresponding learned matrix. It can be seen that the learned structure of the graph is more adaptive and not constrained to physical and psychological constraints, which can give full play on the advantage of graph neural network. AR application. This is a demo of handwriting application in AR screens. A is the control panel. B is the pose of beginning to write. C is the pose of ending to write. D is the handwriting of character ISMA and tremor, showing in the top, showing the bottom, and the corresponding denoted output showing the top. Let's see a live demo. That's all. Thank you.
Thank you kindly. So is there any questions? No? No question? Okay. What's the difference between your method and the common field?
Yeah, our method adopts a novel structure ST spatial temporal graph neural network, which can be effective to extract spatial temporal patterns simultaneously. Yeah, and the experiments verified our method is effective.
Okay. So is there more questions? I have a question. So your method is very fast, right?
Yeah.
So I remember the over 1,000 FPS, right?
Yeah.
Okay.
Our method is fast.
Okay. Yeah, it's great. And then I wonder, is there any limitation or failure case for your method?
Yeah, our method is due to our method adopt solver client architecture for yes, the AR application is a little time delay. The main reason for the time delay is mainly in the data transmission from the server to our client HoloLens.
Okay, thank you. So thank you, Candice, again for your nice presentation. Then the next talk is classifying in-place gestures with end-to-end point-covered learning. The speaker is Li Zhao. Hello, Li Zhao.
Yeah, I'm here.
Yeah, so you can share your screen. Okay. Li Zhao is a graduate student in the College of Information Engineering at Northwest A&F University. His research interests include virtual reality and visual computing. So let's welcome Li Zhao's talk.
Okay. Can you see the screen?
Yeah.
Okay. Hello, everyone. My name is Li Zhao from Northwest Agriculture and Forestry University. The title of our paper is Classifying In-Place Gestures with End-to-End Point Cloud Learning. This work is in cooperation with Xuequan Lu, Min Zhao, and Meili Wang. The walking in place method allows the user to navigate the virtual environment with walking in place gestures, which provide kinesthetic feedback similar to real walking and provide high immersion and naturalness. However, the walking in place approach has not been widely used due to several challenges. The first challenge is to classify gesture patterns that map the user's specific gestures to virtual locomotion.
Hello, Li Zi. That's problem. You may can switch your screen, so you first
sorry.
see your present.
Sorry.
Yeah.
So is this okay?
Okay, perfect. Thank you.
Okay. Right. Moreover, due to the interperson variations, which represent different characteristics of users such as height, weight, gender, and locomotion habits, the method designed may be accurate for some users, but may not work for others. Hansen et al. Utilized the linear acceleration of XYZ axis of the head-mounted display as input and fed it into a convolutional neural network to predict whether the user is currently walking or standing in real time. Shi et al. Attached 3 pressure sensors to the insole to collect pressure signals from users under 7 different gait patterns to create a dataset. They proposed dual-check token census, which is based on improved long short-term memory network for classifying 7 types of foot patterns. However, these methods induce a relatively high latency. The goal of our research is to build a method that can quickly and accurately identify the user's in-place gestures for virtual locomotion. To this end, we first collect locomotion data using the HTC Vive Pro head-mounted display and two Vive trackers attached to the user side, in which each device provides a point at each frame. We treat the data of several consecutive frames as a point cloud sample and build a point cloud dataset by labeling all samples. Each point involves the 3D position coordinates, velocity, rotation, and angular velocity of the user's head or legs. We design a point-based classification network by fusing unsupervised domain adaptation with a point cloud backbone for real-time point cloud classification. We use the sliding window method to segment the whole dataset into point clouds. The fixed window size is 180 milliseconds, which means 6 consecutive frames at a frequency of 30 Hz, and the window step size is 90 milliseconds. The label of the point cloud indicates the ground truth of the posts contained in the corresponding window. Suppose there are C classes of gestures in the window. We choose the class that appears the most number of times in this window as the label of the window. So this slide shows the point cloud data visualization of 9 types of gestures for virtual locomotion. Different point colors denote different tracking sources. Yellow means head-mounted display, purple and green indicates left and right trackers respectively. We train a model for each user. For subject I, we use the unlabeled data of this subject as the target domain for unsupervised domain adaptation, and use all other users labeled data as the source domain for supervised learning. For the data in the target domain, we select 90% of the data as the target training set and the remaining 20% of the data as the target test set. Both source training set and target training set are used to train an end-to-end gesture classification model. The target test set is used to evaluate the performance of the model. We apply point cloud transformer as the backbone and fuse unsupervised domain adaptation. Point cloud transformer uses the neighborhood embedding module to capture the local geometric features of the point cloud and the optimized offset attention module to learn the global features. Inspired by the novel adversarial training strategy proposed by MCD, we use the encoder from PCT as the feature generator and two task-specific classifiers as the discriminator, which takes features from the generators as input. The two classifiers are trained to correctly classify samples in the source domain while detecting target samples that are not clearly categorized into some classes. The feature generator is trained to fool the two classifiers by generating target features close to the two classifiers' decision boundary. In each epoch, we first train both generator and two classifiers by minimizing the cross-entropy classification loss so as to make the network correctly classify the point clouds in the source domain. Then we train the classifiers to minimize the discrepancy loss, which is defined as the difference between the outputs of the two classifiers. Finally, we train the generator to minimize the discrepancy loss. The last two steps use only unlabeled target samples. We select 10 subjects from the dataset marked as S1 to S10. For each subject, we evaluated the classification results after training the individual models separately, except for keeping quoting, the average classification accuracy of all other classes is greater than 92.5%. Compared with other deep learning methods, our method achieves the best result of 95.0% overall accuracy and 94.4% mean class accuracy. Note that a window size of only 180 milliseconds enables an accuracy of 94.4% with 12 milliseconds model inference time, which satisfies the requirement of real-time applications. We conduct a user study using the evaluation testbed proposed by Canvas et al. To evaluate the straight line walking and directional control performance and user experience of our model for locomotion in the virtual environment. This figure shows the user study accuracy results. We can conclude that our method is more accurate than other walking place methods. For example, when using our method, the user can walk closer to the target straight line indicated on the ground and can stop more accurately within the target range. So in conclusion, we present an effective classification framework for classifying non-in-place gestures for virtual locomotion. We propose to treat several consecutive frames as a point cloud, which the HMD and two trackers provide 3 points in each frame. We design an end-to-end method by fusing supervised learning with unsupervised domain adaptation. Experiments show that our method achieves very promising outcomes. We also conducted the user study to further verify the effectiveness of our method. That's all. Thank you for watching.
Thank you. Thank you, Liz. Is there any questions? No question. Okay, I have a question. Is there any a limitation for your work?
Well, for limitations, I think our work needs NVIDIA GTX GPU, and it maybe can work only on PC-based virtual reality devices through the WebSocket. Maybe for mobile virtual reality devices, it cannot work well on that device. So we may fix this limitation in the future. Thank you.
So okay, thank you. So do you have any idea to speed up your math, compress the model, or maybe could you share it?
Maybe in the future we will try the GCM-based method or other more advanced neural networks proposed in recent years. Or maybe we will propose a tiny model to reduce the calculation requirements. That's all. Thank you.
Okay, thank you. So is there any more question? Okay, it seems no. Then let's thank. Okay. Oh, there's a question. Was the window width of 108 milliseconds for the time window processing predefined, or was it tested experimentally?
Okay, thanks for your question. We do some test experiments, and the results show that the window size of 180 milliseconds was moderate for the balance of accuracy and time spent, while other window size may not meet the accuracy or not met the real-time application requirement. That's all. Thank you.
Okay, thank you. So is there any more question? Okay. So let's thank Liz Zhao's next talk. Then the last talk is about the object at hand, automated editing for mixed reality video guidance from hand object interactions. The speak is Yao Lu. Yao Lu is a PhD student in the VR lab of Bristol University. His research interest is the hand-based egocentric systems. Oh, that's welcome Yaolu's talk.
Hello, everyone. I'm Lu Yao from VI Lab from Bristol. My topic is about the segmenting the guidance video with hand cues. So it's a kind of like a content authoring problem in the AR and the VR. So our method has 3 steps. It's really straightforward. The first step is detecting all the hand-object interactions in the video. Like when interacting with the video, we have 2 hands, like left hand and right hand, from the egocentric perspective. And our method is like detecting all the hand-object interactions first, and then for each hand, we use a finite state machine to control the status, and then segment the video for each hand. The last step is like to fuse the segmentation results from both hands together to be one final result. So let me go through in detail. The first step is the hand-object interaction detection. In this one, we use a faster RCN-based method, but in the classification head, we set 6 different kind of classes. So as you can see on the screen, so we have left hand, right hand, and the objects. They both have like 2 kinds of status. One is in action, the other one is not in action. So here is kind of like a picture showing what the classification results. So here is the data set we collected for Chinese team making. We invite 6 participants to perform the Chinese team making process with the instructions. So they perform with instructions. And you can see on the left picture, so there are like classification results. Let me go through detail for you. So you can see, yeah, so on the right is the kind of demo. We detect the hand object interaction. So on the left image, so you can see the green bounding box is the left hand in interaction. It means like the left hand is interacting with the object. And you can see the red bounding box is the object being interacted with, and the blue one is just the normal object without any interaction. So on the right, you can see as well, so the right hand in interaction with the red bounding box being interacted with, and the blue bounding boxes are normal objects without any interaction. So the first step is like detect all the hand object interactions. So we have done that. And for the second step, we will segment the video with this result, with this like interaction detections. So how we define interaction? So it's really straightforward. We first, from the first RCN results, we have the objects in interaction. If we have another hands in interaction, if the 2 kind of bounding box has some kind of like overlapping, mathematically, it's the IOU is like greater than 0. We define this as interaction. So just as the video performs here on the right, so you can see that if the 2 bounding boxes has a kind of like overlapping, we define it as an interaction. So we link the middle of the 2 bounding boxes together, and the hands with the red dot, the white dot is like means it is interacting with the object. So yeah, this is how we define our interaction. So, but for the first RCN results in the video, it can be sometimes fails. Like means it will miss some detection results on the hand or on the object. So to make it more robust, we use a finite state machine to control the status. It's really simple as well. If continuously, if like there are 6 or like T frames has like keep detecting us the interaction, we consider it is like a interaction status. So it's kind of like a temporal information we use to make it more robust. So here is a kind of like example. So we can say on the left, on the left top corner, we have like a score of 10 for each hand. It means like in the past 10 frames, both left hand and right hand has the they both like has score of 10. That means like there is no like false detection in the past 10, and also in the past 10 frames, the hands are keep like interacting with the object. So when the left hand is moving away from the teapot, you can see the left score dropped to 5. So because our threshold is 6, when it drops to 5, the detection status on the left hand is the negative. So it means like the left hand is no longer interacting with any object. So you can see the the white dot on the left hand is disappears. And when the left hand like picking up the lid of the teapot, you can see the left hand score like is the 6, and it means like the left hand is go back to interacting with the object. So so from the second step, for each hand we have pre-segment different pieces of like a video, but still it has some like false segmentation. For example, if I pick up something, there is a false like results in the middle. So it means like the full like the full process will be divided into 2. So that's not it's not acceptable. So in order to overcome this, we use the features of the temporal feature of the object in hand. So here is how it works. From the 2 adjacent pre-segmented videos, the clips, so we try to measure the similarity of the object in hand. So you can see we have the bounding box on objects. So we crop all the bounding boxes, the content in the bounding boxes of the objects, and then save it to the computer. And when in the post-processing, we just like try to measure the similarity. And this is our network to measure similarity. It's quite simple and straightforward, just like we concatenate the 2 images and use the VGG like feature extraction, and then we produce the similarity at the end. So it's really easy to train this network. We just crop a image in the any frame, and then we just move the image, shift the image a little bit, or rescale the image, and resize them together to concat them, and then we produce the similarity as 1. So that's the training process. So in the reality, if there is no much like a difference between the 2 images, the similarity would be really high. Otherwise, it would be really low. So especially in the same environment and situation, so this similarity check is really robust. And by this way, we measure all the similarity between each cropped objects, and then if the similarity is the average similarity is higher than a threshold, we just reconnect the two pre-segmented clips into one. So yeah, that's all happening on a single hand. So the last step is like fuse the results from both hands. So previously we have the results for single hand, but you know, the hand sometimes like they are trying to do something not like this, I mean, separately, or sometimes they are doing things like simultaneously. So it's not really easy to tell which, like where we should segment. So we set up some rules for the segmentation. We defined IOSA as the intersection over the smaller area. The smaller means like the period of time. So as you can see, for the case ABC, it's the IOSA smaller than 0.5. So we can really straightforward to have to come up with which the segment should the segmentation should happen. For the case A, you can see the you can see the red line here to segment the left and the right. So for the B, it's more straightforward. There's nothing overlapping left and right. So C as well. So it's really it has like just little overlapping. So left, right, and left is really easy to separate them. But for the D, E, and F, it's more complex because like the two hand action are like heavily overlapped. So where should we put the segmentation? So here comes another problem. So because when you are doing something, imagine you are doing something, you always put your attention on a single hand. That means like you cannot focus on both hands simultaneously. So we are thinking, how can we find the hand you are putting attention on? So we actually we like manually label the attention hand on the 3 data sets. So on the left one is our Chinese team making data set. On the right one is the really famous action recognition data set application. And the bottom one is another famous data set called GT. So we invite some people to manually label the hands people put more attention on, and then we normalize all the attention hand to the center of the image and draw attention map. So you can see the attention map is on the left. So it's a little bit like abstract for you to see. Let me explain to you. So it means for the left. So here the left one means the left hand attention map. The right one is the right hand attention map. So for the left one, you can see when your hand is on the when we like normalize your right hand in the center of the image, the attention hand is always like be the one closer to you. So we just, this is the heat map. It like indicates the frequency of the attention hand of the left hand. So when we like normalize your right hand to the center of the image, we draw a dot on the left hand. We can see this is the distribution of the left hand when it's being attention. So similarly on the right hand. So actually this attention map like has a conclusion. It's like when you're doing something, the hand like closer to you, it's always like you have like more attention. So by this way we can easily solve the problem of the situation in DEF. Like we just like prioritize the segmentation with the attention hand. So here it is, and we segment all the videos like this. So let me like conclude all the process again. So first we detect all the hand object interactions, and then we like crop all the objects from the interactions and then measure the similarity of them to reconnect the pieces of the clips. And secondly, we try to like segment the clips from the both hands. And lastly, we fuse the two segmentation results from both hands and into one. So that's the way we segmenting the video for the guidance. So there are some limitations. Let me like talk about this. So the limitation is like our method only works with the egocentric perspective, and then we only works like you know, the instruction tasks. So like the human hand should be always appear in the scene. So that's kind of like a limitation our method is. So yeah, I think that's all. So any questions?
Okay, thanks, Yalu's nice presentation. Oh, I see a question. So do you need to update a model to recognize objects, or does the algorithm recognize them as objects through edge detection?
So I'm not sure I got your meaning, but so let me talk about my interpretation. So our method, our like model can handle the novel objects. So in any cases, for example, if there are, because we collected data not just based on our Chinese team making data set, we also label some data from the application and the GT. So it should be it can be generalized to other data sets as well. And we also tested our object detector in the real thing. So but I didn't put the results here, but it does can detect some novel objects. So if your hand is like touching something, the object will be detected as the object being interacted with, and your hand as well. So normally the object detector for the normal object, it's kind of like a general object detector. It doesn't really have any like classes, so it will not classify this as a teapot or like a teacup. So it just recognizes it is an object. So if your hand is like touching it or grabbing it, so have some kind of like overlapping, it will be like classified as an object being interacted with. So I'm not sure I'm clear.
Okay. Is there any more question? Okay, since no, and yeah, the time is already out. Okay, so thank Yao Lu again for his nice presentation. So the 6 talks of this paper session are done. And in the end, I would like to remind that all participants should move in to get the time to talk one-to-one with authors in Q&A rooms. The first talk is in the room of track B1, and the second talk is in the room of track B2. I also would like to remind that all the participants to vote on research demos and the competitions. The details are forthcoming. Okay. So this paper session has ended. Thank you all for your for participating. Thank you.